Oh, hello, I'm Thierry Gaudry from CNRS in Nancy, France. And I'm going to give a talk about some work I did on the Moscow internet voting system. So let's start the screen sharing. That's it. So this is joint work with Alexander Golovnev from Harvard. And also I should thank Julia Krivonozova from Estonia, who basically gave the hints for me to start this work. So here is the general plan, some context, and then a description of the attacks that we found with Alexander, and more general weaknesses in the general protocol. And this was all about a system that was used about 1 year ago, and 1 year later, some other election took place in Russia, and I'm going to say a few words about this recent election. So, what was it? It was in September 2019. It was the day of local elections in Russia. More specifically, in Moscow, they were voting for the city parliament, the Moscow Duma. And this is actually the parliament, but there is also an executive part for the city. And so two distinct powers. And for this parliament, the rules are as follows. There are 45 members, each one elected by one district. And each district corresponds to more or less the same amount of people, about 7 million voters in total. And in each district, I mean, the rules are pretty simple. In each district, the candidate with the largest number of votes get the seat. And that's it. So pretty simple rules. And for the first time, for this kind of election, they decided to do an internet voting experiment only in 3 districts, and but with no restrictions on who could register in advance and then use internet voting. Nothing like only people abroad or things like that. Everybody could register. I mean, everybody from these 3 districts could register and then use internet voting instead of classical. If you remember, it was last year in summer, and it was not exactly a peaceful context. Several protests took place due to rejection of opposition candidacies, and there were protests up to 20,000 participants in Moscow, which is actually quite large. My point is not at all to do politics, but just to mention that when you start experimenting internet voting, it's maybe not easy if done in such a context. Still, they tried to do it properly, and they proposed to a public test of the system. So there was a bounty program, the source code was made public, and various attack scenarios were proposed. These links are clickable, so if you download the slides, you can click on it, and then you will realize that this formulaoffer.pdf, which sounds very much like something you want to read, is actually written in Russian, and I'm not Russian speaker, but I could kind of guess that was going on. So the source code is on GitHub. This is still there. It's called blockchain voting because there is some blockchain involved, as we'll see later. Apart from this source code, which is partial, of course, you don't get all the system. There is no specification, no documentation, and in this formal offer, there is only a description of the things you were supposed to try to test. And these scenarios, attacks, were actually sponsored by a private person, but no, it was not really part of a formal certification process. Nothing like if there are too many problems, we stop or something like that. I mean, it was just, okay, we do the testing and we'll see what comes out. So this is how it went in this summer. So the code publication was was done in July 17, and remember that the D-Day, the day of the real election, is September 8, so only 2 months before, 2 months in advance. And then just after, Julia posted actually on her blog a description of this. And this is actually the way I heard of that, because I'm not following I was not following the Russian press, or I was not aware of this internet voting experiment. And it was actually this blog post by Julia who really got me into this. And it was already the start of the public testing. And it was also midsummer, so actually just before I went on vacation, I had a quick check, quick reading on the source code. I found some weird things, but nothing more. And it's only when I came back from vacation and then the public testing was officially closed that I read again the code, and then I found all the things that I'm going to explain. And I make it public very quickly, first to the organizer, of course, and but then also on archive, because I was really not sure what was going on with this email I sent to the official organizer. I didn't receive anything, so it was a bit weird. But finally, they acknowledged the problem, and there was a first update fixing the problem August 20, so barely 3 weeks before the election. But then, readily, Alexander found another big problem with this updated version, and then there was another final test, August 28. And the final update on the GitHub was done only 2 days before the election. So as you can see, this is all very stretched in time. Just during the summer, they got 2 attacks and 2 fixes, and several tests, at least 2. I think there were even one more. And so very, very short. So what was the first attack? First, so it is all about it was all about the encryption scheme, and this encryption scheme uses some variant of EIGamal. I'm just going to recall EIGamal, not because I assume that you don't know it, but because it's easier for me then to describe the variant they use and how to break it. So we start with Z over PZ, where P is a safe prime, and G generator. SK PK is a key pair where PK is G to the SK, PK is the public key, and plain EIGamal encryption of message aim. M should be a group element, is as follows: is an A-B pair where A is G to the R, B P to PK, public key to the R times the message, where R is a random that must be used only once. The decryption is if you know the secret key is key, then this is B, the second element of the ciphertext, times A to the minus SK, and then you can check that you recover M. And if done correctly, if the TTH is hard in this group, then this gives in CPA security, which is not exactly the full encryption security one, but still not so bad. So what did they use? In the original scheme, the original source code they published, there is actually a multi-level variant of EIGamal. You choose 3 primes, P1, P2, P3, 3 safe primes together with 3 generators, G1, G2, G3, and actually there are 3 key pairs grouped into a pair of triples. So the secret key is SK1, SK2, SK3, 3 independent randoms. And the public key is then G1 to the SK1, G2 to the SK2, G3 to the SK3. And with these multi-key, the encryption of a message goes as follows. So the message M should be then over P1Z, so the first group. You apply EIGamal with your first key to it, you get A1, B1, and then this A1 that belongs to Z over P1Z, you map it to Z over P2Z, so that you will actually be able to encrypt it with the second key. That's what you do. You encrypt A1, you get A2, B2, you map again A2 to Z over P3Z, and you can then encrypt again A2 and you get A3B3. So the multi-encryption of your message will be actually all these A1 and A1, A2, B2, A3, B3, except A1, A2 that you don't publish. So basically you have A3, B3, the final EIGamal pair, and then B1 and B2, the second part of the partial, the over encryption. So it's a bit weird, but why not? And maybe I should mention that all this weird mapping from group to another is done by canonically lifting to Z. You take an element of Z over PZ, you see it as an integer, and then you reduce it modulo over P. By the way, all of this is just taken from the source code. There is no documentation I could find describing this as I write it. So and in particular, the mapping, explicit mapping from one group to the other, was all implicit in the code, of course, using integers for the time. So decryption, if you know the SK goes easily, you just reverse everything, and with A3B3 you can recover A2, and then you, since you know B2, you can decrypt A2, B2, get A1, and since you know B1, you can recover M. And due to the fact that P1, P2, P3, all these mappings that we have won't destroy information, then they work fine, and this works. This really decrypt. Okay. What about security? Then here is the problem. Of course, contrary to triple-DES, which was maybe an inspiration for that, we had a number of operations to break the system squared. Here, this is just multiplied by 3. Basically, have 3, well, just like in the picture before, you have the 3 small locks instead of a big one, and breaking the 3 locks independently is enough to break the system. So we are basically left to break 3 underlying EIGamal independently, and these are small EIGamals, P1, P2, P3 are small. So why did they do that? I didn't get the final answer actually, but I speculated. And the thing is that all the PIs are chosen to be less than 256 bits. And this is enforced in the source code with tests that look like that. They compare P to the solidity max int constant, which is 256 bits. And solidity is the smart contract language used by Ethereum-like blockchain. And indeed, in the code, there is a decryption function written in this smart contract language, which is maybe a bit weird, but well, that's like this. They wanted to use the blockchain, and it really looks like the author did not have the time or maybe the competence to write a multi-precision library in Solidity, and they decided to increase the security in another way using the same kind of thing that we did with triple-DES. So yeah, I guess the why did they use that? Probably this is due to the blockchain that they have inside the protocol. So we are now left with so the problem of computing discrete log modulo prime p of 256 bits. We have to do it for the 3 different p's. Well. And the challenge says that it must be done in less than 12 hours. And 12 hours, okay, we'll see. But 256 bits, that's certainly something that has been done before. It was done in history very early, actually. And we can, I don't know if you remember when it was done. If not, you can check in this DLDB database that we host in my institute. And then in this database, we can see that the first public record for this kind of size was done in 95, 96 by Weber, Denny, and Zeiger. So it was a long time ago, 25 years ago. And if you compare to what is feasible right now, the current record is almost 800 bits. And it has been announced in December by a couple of friends and myself. And it will be actually published at Crypto tomorrow. It took about 3,000 core years, or equivalent of that. So the question now is how much time does it take to do 256 bits today? Because of course at the time of Weber-Denny and Zaire, it took a lot of time with very simple machines. And the question is, does it take less than 12 hours? Let's have a look at the available software for discrete log in Z/PZ. So first, SageMath, which uses JP-Parry internally for DLP. So this is free software. This is not bad at all for small size bits, but for 256 bits, it did not finish after 4 days. So I stopped it there. I don't know how long it would take. Maybe not so much more, but well. I tried with Magma, which is proprietary software developed and sold by University of Sydney. It's faster than SageMath, but uses a lot of memory, especially for the linear algebra part that they have in their algorithm. And for 256 bits, it's finished actually in 24 hours with 130 gigabytes of memory. So a bit too much compared to the challenge that lasts 12 hours. And also, this is really an implementation that is mono-threaded. So it's not, I mean, it did not look easy to reduce this work time. And then, of course, I used CADO-NFS, which is the software that we developed mostly in Nancy for doing our record computation. And this is based on the number field sieve. So while the other ones are based on the asymptotically slower algorithm. And this was used for the latest record, as I said. And actually, when I tried it for these sizes, it took less than 10 minutes and less than 1 gigabyte. So that's it for 256 bits. It's really, really faster than what they expected. So here is a bit more detail. Running times. So I just used the desktop PC I had on my desk this day, and nothing special about it. And so as you see, this is something like 10 minutes, and with each line includes actually 2 runs of CADO-NFS, one for computing the discrete log of the generator and one for the discrete log of the public key. With NFS, actually, you don't get, you need those 2 things unless maybe the generator is the small element that is already in the factory. But despite having to run it twice, actually, if we use the same P, so then many steps can be automatically shared. So that's, each line was just pretty fast. And I should mention that the variation from 1 key to another, as you can see, from 300 seconds to 500 seconds, is not unusual for computation of this small size. Actually, for larger sizes, for record computation, this is no longer true that you have these variants. This is really due to variation in the time taken by steps that become negligible for large sizes, like computing shared robots, for instance. I wanted also to mention that this size was not thoroughly tested in CADO-NFS, and sometimes it failed due to bad parameters in the descent phase. So it was quickly fixed for this occasion. That's it. So I made this public very quickly after I found it. I wrote a blog post, a note that I put on archive, and actually, of course, I mentioned that to the developers. And as I said, on August 20, they did an update. So what did they do? First of all, they removed the triple-EIGamal encryption. Second, they increased the key size to 1024 bits. And third, maybe interesting part, kind of confirming my guess about the smart contract thing, they changed the protocol so that decryption is no longer part of the smart contract. So triple days, smart contract, away. And something that is also interesting is that I just had a remark in my note. I said, oh, by the way, this is a bad idea to take a generator that is not in a prime order subgroup. They took actually G, G1, G2, G3, and generator of the full Z over PZ star group, which is bad practice because you could leak something. So they changed that to take a generator in a prime order subgroup. So that was it. Then, a few days later, Alexander Golovnev had a look at all of this, and he also was happy to see that the generator was now in a primary subgroup, but he realized that the messages are not. They were just random elements in the, well, not exactly random, but elements in the full Z over PZ star group, multiplicative group. And then actually one bit is leaked, because from the ciphertext, one actually knows easily if the message is a quadratic residue or not. So you get one bit of information about the message. And from the source code, actually, the encrypted message is exactly the identifier of a candidate. There is no randomization at this stage. So this message is actually an identifier, a number, a 32-bit number that identifies your candidate. And there is no guarantee that it's a quadratic residue or not. And quite often in e-voting, one bit is the whole answer, actually. Because imagine this typical scenario, you have two main candidates, one is for Putin, the other one is for the opposition. Then if one of these candidates has an ID that is a quadratic residue and not the other, then actually from the ciphertext, you know the clear. So it was the remark of Golovnev. And from this, I did not really understand what was going on. A lot of things were got in the press, but in Russian, and it's not so easy to understand what was going on. The developer seemed to deny that this attack was a real one, but still they changed the source code without updating the GitHub. So how did we realize that? We knew that because a final public test was done, and from the minified JavaScript that was sent to the voter, it was kind of clear that before encrypting the message, they were squaring it, so that actually the attack would work. And then after decryption, they took the square root and decided the sign from the size of the identifier. So yeah, it was changed silently, and only 2 days before the election, the GitHub was updated. So basically, they finally acknowledged that it was a problem because they changed the source code. What else do we have in this protocol? So, as I said, now, I mean, after they fixed this subgroup thing, they had already fixed the key size. So instead of having a really weak encryption, they have an encryption which is kind of okay. And but weak encryption is one of the easiest things that we could really analyze from the source code. Without specification, it's pretty hard to analyze the other very important properties that you need for internet voting. I mean, encryption is something, but it does not give you per se privacy. I mean, it really depends who gets the key, how is it encrypted, how it works. And for all of these more advanced properties that you expect from voting, from internet voting, we just speculated based on discussion, press article, a bit of source code, and our general impression is that everything is kind of wrong. Privacy, there is no real privacy. I mean, usually when you ask for privacy, you ask with respect to whom to trust and things like that. And here they seem to trust much more than what is expected in e-voting. They trust the server, the web server, they trust everything. And it's kind of annoying. Verifiability. So this is a very important property in e-voting. People should be able to check that their vote is really taken into account. And for that, they have partially positive answer with this blockchain they used. There is some kind of verifiability. but very partial. I will explain a bit later. And coercion resistance is very important in such a context as in Russia, where people don't really trust the system, it seems. And then you want people to not to be able also to sell their vote, and for all of these high-level properties, it was not taken into account in the system. So basically, with this correct, strong encryption now, they are happy, but the rest is really, really weak. Let me try to summarize a bit how this full protocol works. You have a registration authentication of the voters, which is based on an existing infrastructure that they have for administration in Russia. And as far as I know, there is no real problem with that. This is not specific to this election, and okay, it's probably some problem, but probably not so bad because it's used for, it has already been used for years. The voting itself goes as follows. The voter connects to the server, gets the JavaScript, and the choice of the voter is encrypted locally by the browser with the key, the public key of the election, and then is sent back to the server encrypted. This part is quite classical. Then there is a ballot box, and the server that receives this encrypted ballot sends this to the blockchain. So the blockchain actually holds the ballot box, and there is no reference to the voter, and this is in kind of random order. The server batches a few votes, then randomize the order before putting them in the blockchain, so that you cannot really track from the time. Then at the end of the election, the trustees who own the decryption key, they use sharing secret sharing for that, decrypt the ballots and put them in the blockchain as well. So if you read that, maybe it looks a bit classical, but then read the last line, they also published the decryption key at the very end. So the trustees who had kept secret this decryption key, then they published it at the end as a way to verify that the decrypted ballots corresponds to the real ballots, which is really, really rare, I tell you. But in fact, for the designer, this encryption, the role of this encryption was not really privacy. Privacy is supposed to be guaranteed by the server cutting the link between ballot and voters. And encryption is here only to protect against revealing the partial tally during the day, because you're not supposed to know during the day how many votes already got to one guy or to the other. So this is really just for that. And privacy is just, as I said, by cutting the link between ballot and server on the voter. So you really assume a lot from the server, because you assume that the server, I mean, the server has to know who is the voter, because he has to check the eligibility. He knows the encrypted ballot, and he has to blind itself and say, oh, okay, I forget the name of the voter, and then I forget the ballot. It will be in the blockchain in a mixed order. So he has to forget a lot, which is pretty hard to implement. Forgetting due to all the backups, the redundancy that you need, forgetting for the server is really, really a hard thing to do. So usually we don't rely on that for privacy. This is a bad idea. Further remarks on the blockchain. We have still no idea why they wanted to have the decryption made in smart contract. No clue at all. For me, there is no win by doing that compared to other classical things with zero-knowledge proofs, for instance. So second thing, more critical, the blockchain is a private one, so it provides no guarantee whatsoever. I mean, private. I mean, the whole point of a blockchain is to be distributed and to have so that if someone cheats, then someone else will see that. But if everything is private, well, it really depends on who are the different nodes. And so during the election, the voter could query the blockchain, of course, but only via a web server and check that their ballot was there. So you needed to trust the web server to be honest on this way between the blockchain and voters. Another thing I wanted to mention is that the interaction with this Department of Information Technology in Moscow, who designed this protocol, was a bit frustrating. They answered only some of my technical questions and only basically those that were not embarrassing. Real questions, they were just ignored. And of course, I asked many times, could I get specification, documentation, and could not get proper answer on that. What occurred on the final day, on the voting day? So they did not cancel the use of internet voting, despite all these very last-minute changes. And in total, 10,000 votes by internet were cast. So not so much, but not so few either. And in one of the districts, actually, the difference between the first and the second candidates was less than 100 votes. So actually, this 10,000 votes by internet, so this 10,000 was for the 3 districts, but still, on this district, it was internet votes were more than enough to change the result. An interesting thing is that a few hours after the election, the access to the blockchain was cut. And which is really weird and defeat the purpose of having a blockchain. I mean, if someone controls the access to the blockchain, that means that it's not distributed anymore. So why do you have a blockchain instead of just a central server? No idea. So fortunately, the journalist of Medusa online newspaper, so this is exiled in Riga, they made a copy of the blockchain of all the ballots before the shutdown. And they also got a copy of the decryption key. And with this, actually, and one of a journalist of this newspaper, he was a voter for this election, and he kept track of all his network connection between his brother and the server during the voting. And then with this blockchain data that they managed to copy, he could indeed check that his ballot had been taken into account. So there was some kind of verifiability if you were clever enough to log all your communication and then to really get a copy of the blockchain before they cut it down. So of course, you don't expect this kind of skills from a layman voter. Just vote and then in the end wants a simple way to check that her vote is really there. So, small conclusion about this this work that we did with Alexander Golovnev and the encryption scheme. The main impact was not really that they fixed the encryption. I mean, there are many problems in many places. But we kind of publicly showed that it was not the perfect scheme as claimed. And this got a large press coverage. And for that, I really thanks Medusa, this online newspaper. And Moscow really had to acknowledge the problems. And hopefully this made some voters skeptical and they decided to use traditional voting. And hopefully the organizer or Moscow in general got some pressure to do a better system for the next experiments. And that was our conclusion last year after the work. And we wanted also to have a positive note, like opening the source code and doing public testing was really a good thing, and quite amazing actually to have this in Russia, while in many countries this is not done at all. In France, for instance, in my country, this is pretty hard to get any information from e-voting that is done for public political elections. So really it should be commended to have this kind of public thing. But let's see what went on 1 year later. 1 year later, so this is just 1 month ago. You probably heard about this very important voting in Russia, but the change of the constitution. It was so end of June, beginning of July, and several political or social amendments were put to the vote. and all Russia was voting. And again, internet voting was possible, and this time it was much larger. It was possible for all the residents of Moscow and from the region of Nizhny Novgorod. And again, the voter who wanted to vote by internet must register in advance, and then during the first few days of the election, they could vote by internet. And what kind of systems were used? Again, it was designed by the Department of Information Technology in Moscow, but this time the code is no longer public. And I got the information that they used Lipsodium for encryption, which is good. I mean, this is really a much better idea to use some kind of off-the-shelf crypto library instead of trying to reinvent their own stuff. They still use some blockchain, and this time this is an Exonym blockchain. Exonym is some framework for doing private blockchain. So obviously, it's again private blockchain. And again, no documentation, no specification, no idea how it works. I asked it and I got no answer, of course. And this time, I didn't have time at all to try to get more information, try to investigate how the system worked. So I don't know exactly what's in this system, but some article in the press cited Dmitry Chesnik, who studied a bit more of this system, and according to him, there is absolutely no coercion resistance. He also mentioned some weird things, like they use Lipsodium in a way so that the voter and the server would actually do a full key exchange for casting the vote. So actually each vote, each ballot would be encrypted with some kind of Diffie-Hellman key exchange between the server and the voter. And then I really wonder how they can decrypt that thereafter without keeping track of all these keys. I mean, it's, well, I don't know. This is again some weird system, and but I can't say more actually. And is there something to report after this vote? Well, what follows is really based only on automatic translation of Russian press. So maybe I got something wrong, but what I saw is that there was some massive use of e-voting. Moscow got 1 million e-ballots cast, and the other region, Nizhny Novgorod, who did this internet voting experiments, got 130,000 e-ballot casts. So as you can see, this is in Moscow and in this region, between 10 and 20% of the voters who used internet voting, which is huge. This is massive. And this is not at all negligible if you take into account the total number of ballot casts in Russia. A few percent of the votes were e-ballots. There were also accusations of fraud and coercion, but most of these accusations were not really on the internet voting, on the e-voting part, except a bit about the coercion, where people were seems to have been forced to register and then to vote with the e-voting system. But there were really some accusations of frauds based on statistical evidence of ballot stuffing. See, for instance, this link. This is a bit frightening. You see some spikes that should not be there. And, wow. Anyway, what kind of conclusion can we draw from this last experiment where they used again e-voting? So, despite our finding of last year, e-voting in Russia is still based on far from satisfying system. I kept insisting on having public documentation, and but it's not yet there. And this is really a key feature for an e-voting system. Having the documentation public is important. Otherwise, how can you have verifiability if you don't have, if you don't know how the system works? There is no way to check verifiability, and the same for privacy. You just have to trust, and the trust is not really there in Russia these days, it seems. So none of the usual properties guarantee, no coercion resistance, which is really a big problem in a country where there is no such trust. And but really, so usually when it comes to that, my conclusion would be, well, stick to the traditional voting system. Don't use e-voting for a high-stake election. If you have something that works with polling station, then use them, stick to them. Don't use internet voting. It's not really, it's difficult. Having coercion resistance is really difficult in practice. So don't use it for high-stake election. But in that case, in the present case in Russia, where you don't have trust, you also have problems, allegation of fraud and coercion in the classical thing. What should we recommend? It's pretty hard. I mean, maybe it's actually easier to monitor, to help, and to push them to get a better e-voting system, so that it reduces the risk of fraud. And so, yeah, in this situation, honestly, I don't know if I recommend or not to continue these experiments with e-voting. Of course, if they do, they should really go the classical way of having public documentation and trying to have as many property as possible. But, well, I'm not comfortable in saying the usual conclusion that I have in France, for instance, when I say I don't use internet voting for high-stake election. We have pretty good polling station system in France for high-stake election, so why stick to that? And so, yeah, I leave it, I guess, to your thinking. And should we help and push the Russian community to have a better e-voting system, or should we just tell them to stop that and stick to a real election, real physical election? I mean. Okay, and with that, I'm going to stop with this talk, and I thank you for watching it. Bye-bye.